In this paper, we studied the problem of maximum clique computation over sparse graphs. This is because real-world graphs are usually large and sparse. Existing studies are divided into MCC over dense graphs and MCC over sparse graphs. The MCC dense problem has been extensively studied. Existing MCC dense solvers rely on the adjacency matrix graph representation, so they cannot handle large graphs. These solvers use recurring for bounding and degeneracy-based branching, whereas existing MCC sparse solvers use the adjacency least graph representation to handle large sparse graphs. They can also handle dense graphs, but usually much slower than MCC dense solvers on dense graphs. These solvers use coloring for bounding and highest color-based branching. Our initial investigation shows that adjacency matrix is good for recursively working on subgraphs. It also shows that recoloring-based bounding is generally better than coloring-based bounding. Also, degeneracy-based branching is generally better than highest color-based branching. In our paper, we transform MCC over a sparse graph G to K-clique, finding over small and dense subgraphs of G. We also incorporate adjacency matrix, recurring-based bounding, and degeneracy-based branching for KCF dense. Also, we introduce reducing techniques for KCF dense. This is the workflow of our algorithm. We first invoke MCDD to compute an initial clique and an upper bound. If the initial clique size equals to the upper bound, then it stops at stage 1. The running time is OM and the graph is an extremely easy instance. Otherwise, we invoke MC_equal to compute a refined initial clique and a refined upper bound. If the refined clique size equals to the refined upper bound, then it stops at stage 2. The running time is O theta G times M and the graph is an easy instance. Here, the theta G is the degeneracy of G. Otherwise, we invoke MCBRB to compute the exact maximum clique, whose worst-case running time is exponential. We have tested our algorithm MCBRB against the existing algorithms PMC, BBMCCSP, and RMC over 19 real-world graphs. The second column of this table shows the maximum clique size of the graph. Across all the graphs, our algorithm consistently outperforms the existing algorithms. Among the 19 graphs, we can see our algorithm finishes in linear time for 6 graphs shown in red in the table. That is, it stops at stage S1. For another 4 graphs shown in blue in the table, our algorithm finishes in near linear time. That is, it stops at stage S2.